So, hello. I will first explain the paper a bit because the paper is kind of badly written. So, I had a problem with understanding it. So, first I'm going to explain it. And the paper, I mean, the mathematical model which I'm going to explain is implemented in the function sensitivity control. So we are not going to take a look at this function because it basically implements everything that's described in the paper. First, I want to explain where does this equation come from. So let's go to Paint. So if we take a look at the basic equation of the Newton-Raphson load flow, it says that the changes in the active power injections, delta P and delta Q, uh, can be expressed using the Jacobian matrix and using the phase angle deviations, so delta T, and the voltage deviations, delta V. And the Jacobian matrix has the form J1, J2, J3, and J4. So if we take a look at this equation and in the power system's perspective, the submatrices J2 and the submatrix J3 can be neglected. So these matrices are usually considered to be zero, which means that the influence of the voltage deviations on the active power flows is neglected, and that the influence of the phase angle deviations on the reactive power is also neglected. The second equation yields delta Q is equal to J4 times delta V, meaning that the submatrix J4 connects the voltage deviations across the nodes in the network with the reactive power changes in the network. So if we go back and take a look at our example here, we can see that here we have a matrix which connects the reactive power changes with the voltage deviations. So if we go back, we can see that the S matrix, which is being used in the paper, is none other than the inverse J4 submatrix from the Jacobian matrix. This matrix S relates the voltage changes with the reactive power changes in the network. Furthermore, what they did in the paper is that they divided the voltage vector, the voltage deviation vector, into the deviation of the load buses and the voltage deviations of the generator buses, meaning that this S matrix also changes its shape into the SLG, sorry, SLL, SLG, SGL, and SGG, connecting the voltage deviations in the load nodes and in the generator nodes with the respective reactive power changes, delta QL and delta QG. So if we go back at the, sorry, I think there's a faster way to select this. Yeah. If we take a look at the first equation here, so we can say that the voltage deviations delta VL in the load nodes can be expressed as SLL times delta QL plus SLG times the delta QG. And these values, SLL and SLG, these matrices, are calculated from the Jacobian matrix simply by determining its inverse matrix. In the secondary voltage control, the system operator and the voltage regulators in the system have access to the voltages of the pilot points. The goal of the secondary voltage regulation is that the deviation of the voltages in the pilot nodes is equal to zero. So that is the goal of the secondary voltage regulation. Basically, the voltages of the pilot nodes can be expressed by multiplying the voltages of the load nodes, so delta VL, with a matrix C. And the matrix C is given here as a 0, 1 matrix, which says basically that if node J is considered the pilot node, then the value ij will be equal to 1, and otherwise it will be equal to 0. If we multiply this equation, so let me just delete something. So if we multiply this equation with the C matrix, it yields C times SLL delta QL plus the C times SLG times delta QG is equal to 1, to 0. So basically, if there happens a disturbance, and disturbances always happen in the system in terms of reactive and active power changes in the network, that means that delta QL changes. So the change of the reactive power of the generators, which is needed to to completely smooth out these voltage deviations. And so basically, when reactive power change in the network occurs, the changes of the voltages in the network also occur. So to smooth out these changes and to balance, to remove these changes in the voltage deviation, in the voltages across the network, the generators need to be operated in a manner which yields from this equation. So basically, we can call this matrix M, and this matrix can be called N or B, as they used it in the paper. So basically, the generators need to be operated in a manner delta QG is equal to minus B to the minus 1 times M times delta QL. And this operation of the generators will completely neutralize these changes in the reactive power of the loads. So the voltages of the pilot buses will be equal to, so the deviations of the voltage in the pilot buses will be equal to 0. The goal of this paper and the goal of what we've done here is to determine the locations of the pilot nodes, which result in the minimization of the load bus deviations. So basically, when these changes in the reactive power of the loads happen, there exists a question of whether our generators have enough reactive power reserve in order to smooth out and to neutralize these voltage deviations. And the goal is to find those pilot points which, if we control the voltages in those points, then the voltage deviations across the whole network will be normal. So basically, when we determine how to operate the generators to neutralize the voltage deviations, we return this reactive power of the generators into the first equation here, and we get the voltage deviations across the whole network. The goal and the objective function, which we are going to be using, and which they used in the paper also, is to minimize these voltage deviations. So delta VL. So the goal is to minimize them. And to minimize delta VL squared, because this makes our problem convex. So the goal is to find the vector x, which is basically the integer vector, which states the locations of the pilot nodes, which minimizes these voltage deviations. And furthermore, because we have 9 scenarios, so peak, off-peak, and middle load combined with the peak, off-peak, and middle generation from the PVs, we have 9 scenarios. So we have to minimize the voltage deviations across for every scenario. So we have to find the vector x, which minimizes the deviations for every scenario from 1 to n, where n is 9 in our case, which minimizes the voltage deviations for every single scenario. So this is delta VLI, stating that these are the voltage deviations for the ith scenario. We can give a probability to each one of these scenarios. However, I wouldn't do that. I mean, that's my logic. Why would we do that? Because so why not to use this probability? Because we want our pilot nodes to be good for every single scenario, no matter the probability at which it can occur or not. So, because there are some sunny days where the solar generation happens, and there are some cloudy days when there is no solar generation. So each of these scenarios is probable. So we want our system to behave well in all of these scenarios, and we shouldn't emphasize a single scenario over another. That's the idea of the control technique, and this control technique was implemented in the sensitivity control function. In the paper, I just wanted to explain this. So here we were using this disturbance, so the disturbance of load reactive power across different load nodes. So in the paper, they've used it. So let me just find it somewhere. So the disturbance variables delta QL are modeled by a vector of Gaussian random variables with means equal to 0 and standard deviation proportional to the reactive power of the load buses at a certain operation state. What we done here, and let me just show you that in the main function, it doesn't make sense to use different delta QL in every iteration. So for what we want, to just generate a single disturbance and use that disturbance in every scenario, because it doesn't make sense to change the disturbance in every scenario and change that disturbance in every call of the objective function, because our genetic algorithm wouldn't converge. So what we are doing here is we're generating disturbance. Let me just find it. So we're generating a disturbance, a Gaussian disturbance here, and we're using that value of disturbance throughout the whole process. As you can see, we're doing the same thing that they're doing in the paper. So we're generating a Gaussian disturbance which has zero mean and the standard deviation equal to the value of the load of reactive. So this is the reactive load in that particular node. Apart from that, the one thing that we've done different from the paper is that we are not using the partitioning scenario. So what they did in the paper here is that they used the partition. So they determined the optimal partitioning of the network, and they've assigned a single generator, which is a PV bus, to a single partition. So what we are doing here is that because in this network that they are using, they have generators which have a sufficient regulating range in terms of reactive power. In our case, we are using the PVs. So PVs don't have a wide regulation range in terms of reactive power. If we take a look at the PVs, they have some power. So the power of the PVs is, for example, let me just delete this. So the power of the PVs can be expressed, for example, with the variable P. So let P be the generation of the PVs. The inverter, which connects the PV with the grid, has the power S in. So this is the apparent power of the inverter. and the apparent power of the inverter is equal to the square root of the active power given by the PVs plus Q squared, which is the reactive power which the inverter can give us. And basically, if the generation of the PVs is equal to P, then the maximum reactive power which our generator can give is equal to Q S inverter, which is the nominal inverter power, subtracted by P squared. So based on the reactive power which our generator can provide which our PV and in our inverter can provide is dependent on the power given by the PVs. Because of that, and because of the fact that our PVs don't have a wide operating range in terms of reactive power, we can't use this partitioning scenario. However, this is not needed at all. What I've done here is that I've assumed that we want to determine 10 pilot nodes. And in the paper, and if you take a look at these equations here, you will see that the number of the pilot nodes has to be equal to the number of the control nodes. So basically, what I've just done is that I've selected 10 pilot nodes and I selected 10 control nodes prior to that. So, and the 10 control nodes are the nodes which have the biggest reserve of reactive power. And what do I mean by that? Simply the PVs which have the highest the PVs which have the highest power have the highest inverter power, which means that on cloudy days and on the days when there is not enough generation from the PVs, these inverters and these generators can give us the most reactive power. That is easy to understand. So basically, every solar panel has an inverter, and the bigger the solar panel, the bigger the inverter. Meaning that the bigger reactive power reserve. So basically, we in the paper we've chosen, and in this work we've chosen the control nodes. So we've chosen 10 control nodes, and these control nodes are nodes with the highest installed PV power, meaning that they can provide the biggest reactive power reserve and can have the biggest benefits on the power system operation in terms of voltage regulation. That is done in this part of the code here. So we've just chosen the nodes which have the highest installed PV generation as the control nodes. But what you need to take into account that this doesn't matter much. These control nodes, we don't have to use them. We can use different control nodes if you want to use different. However, I think that this is the most logical thing to do. So basically, if we have a PV which has high power, that means that that PV can give us the biggest benefits in terms of voltage regulation. One more thing to mention is that in our case, because we are using unbalanced system, so we're not using a balanced system, which is as this one. We need to determine the way to determine these matrices, so to determine the sensitivity matrices, because this technique is developed for balanced systems. So what I've done is I've just created 3 single-phase systems, so phase one corresponding with phase A, one corresponding with phase B, and the third one corresponding with phase C. For each one of those systems, we determine the PV generation, we determine the control nodes, and we determine the pilot nodes. And then what we're going to do when we merge this code with the code we've done earlier, we are going to just say that phase A has these control points and these pilot points, and it's the same for phases B and phases C. Now let's go to the code. So let me just explain you. So here I changed the code a bit, which generates the data, and so I might as well show you how to play with it and how to change your own network. Basically, if you want to use a different network, but I don't recommend using bigger networks than this one. I think that this is too much. And I think that you should resort to smaller networks, because it's simply easier to see if the results make sense, and if the results and it's easier to implement the codes. I mean, the code is the same. However, it's much easier to show the results and to see if the results have any sense. So basically, if you want to add another network, what you need to do is to change these matrices. So this is the starting node of the branch, this is the ending node of the branch, this is the length of the branch, and this is the configuration. And the configurations are given here. So you need to generate the data in this form in order to use this code again. Basically, when we are converting this three-phase system into three single-phase systems, phase A, if we're taking a look at, for example, the configuration one, so the configuration one, phase A has resistance of 0.4576. And we neglect the resistance and the impedance and the capacitance between different phases. So if we're taking a look at, for example, the phase B, then the resistance of phase B is equal to 0.46666 for configuration 1. So basically, we're just taking a look at R11, R22, and R33 for those three phases. And the same thing goes with the reactances and the susceptance of the network. Furthermore, as far as the loads are concerned, here you can see that this is already done for us in the site where I took the data from. So basically, every node, every node, and in every phase has its active and reactive power determined. So this is already done for us, the partitioning into three different systems. Now let's go to the code. The main function, basically, here you see that we're using this warning off. So this is because the matrix which we are using here, where is it? So this B matrix is often sparse. During the process, it's often sparse, and its inversion it's close. The matrix is badly scaled, so its inversion is sometimes completely. It's impossible to determine its inversion. So in order to solve this problem, and in order for MATLAB not to generate any warnings, we just use warning off, which turns off the warnings during the simulation, because we're calling the objective function where this matrix is inversed a number of times. We don't want our MATLAB to give us warnings every time we do that. Here you have a phase flag. Phase flag is basically just determining which phase you're going to simulate. So phase flag 1 equals that to phase 1, phase A, phase B equals to 2, and phase C equals to 3. So if you want to determine the pilot nodes for phase B, you basically just change 2 here, and everything else will be done in MATLAB. So this is just loading the network data. So the network data along with both the phase A, so phase A contains the lines and the loads, and the phase A PVs contains the PV data, meaning it contains the PV nodes and it contains the PV powers, and it also contains the nominal inverter power, which we have to use in order to determine the generation, the reactive generation of the PVs. So basically, the important thing to notice here is that here we are determining the node types. So in the paper, what they've done, they were using, because they were using a system which has large generators, which have a wide range of reactive power operation. So they've considered the nodes, they had PV nodes, meaning that these nodes have constant voltage. However, because we don't have wide operating range in terms of reactive power, we don't want to simulate any PV nodes. What we've done here is that we've considered every node in the network except the slack node, which is the first node, which is basically giving power to the distribution grid. We consider that node a slack node, and every other node is a PQ or a load node. Or a node with constant power. What we've done here, so here we determine the node types, and after that we sort and renumerate the nodes. Basically, why are we doing this? Because if we take a look at this matrix, we can see that these nodes, for example, here we have node 149, here we have node 1, and the nodes are not numbered in order. So some of the nodes are not here. So because we have nodes like, for example, 113, 300, 450. So we're enumerating the nodes in order for this to be completely logical. So for this to be 1 to 2, 2 to 3, 3 to 4, and 4 to 5, and all the way to the end. So that is why we're renumerating the nodes. And furthermore, because we're simulating an unbalanced system, some of the lines have only one phase. So some of these nodes, which are mentioned here, are not, they don't exist in every phase. So for example, this node, for example, doesn't exist in all three phases. Rather, it exists just in a single phase, for example, phase A, phase B, or phase C. So that's why we need to renumerate the nodes. And this is basically just cosmetic stuff. This is nothing important. After that, we need to set the parameters needed for our genetic algorithm to run. So the fitness function, we're going to take a look at her next. So the number of variables is of course equal to the number of pilot nodes. The number of pilot nodes, I've set the number of pilot nodes equal to the number of control nodes. So this is a condition which has to be met because this matrix here, let me just show you. The matrix B here and the SLG, so the matrix B has to be the size of pilot nodes times pilot nodes. So the size of its pilot nodes. And because here we have the nodes we have the sensitivity matrix which connect the loads with the generators, and the generators are control nodes. So for this matrix to be invertible, the number of the generator nodes or the control nodes needs to be equal to the number of pilot nodes. So don't forget that. Like I said, 20% of the PVs are chosen as the control PVs, and I'm not sure the number, so I think it's 10. And then to each one of those PVs, and to each one of those control nodes, we assign a pilot node, which is given here. That's it. And furthermore, we don't have any equality constraints, and we don't have any inequality or equality linear constraints. We have the lower bound of the variables. So the lower bound of the variables are ones. So because our problem is mixed integer linear programming. Why is that so? Because our variables are integers. So integers which have a range from 1 to, for example, number of PQ nodes, and the number of PQ nodes is equal to the number of nodes minus the number of the control nodes and minus 1 because we have one node which is slack node. These upper bound for each one of the variables is equal to the number of PQ nodes, meaning that the variables of our problem take the values from 1 to the number of PQ nodes. And then we use the variable, so the variable x, which is the optimization variable in the fitness function, sorry, not in the fitness function, rather in the sensitivity control function, to determine which pilot nodes we are going to be using. So we have a set of pilot nodes, which is equal to the set of PQ nodes in the network, or equal to the number of the load nodes in the network. And out of that set of nodes, so out of the PQ nodes in the network, we take the nodes which indexes are given in the pilot nodes vector, which is our variable x. The integer of course, the integer constraint needs to be set, so every variable is an integer, and we have a nonlinear constraint here, which is very important to notice. So it's a simple function, but it does a really important job because it allows that our variables. So if we take a look at, for example, let's describe this. So if our vector x is equal to 1, 2, 3, 4, 5, that's okay. But if on the nodes, the pilot nodes can't repeat, so we can't have two same pilot nodes. So this is what this part of the equation does. And what this second part of the equation does, so this is a nonlinear constraint. This should be logical. So basically, we have a network which has 123 nodes. This assures that the first, for example, pilot node can be 1, but the second can't be from the range 1 to 5. So basically, we want our pilot points to be spread out across the whole grid, because we have 123 nodes. We want our pilot nodes also to be spread out across the whole grid, so we don't get a situation so that our pilot nodes are, for example, 1, 2, 3, and 6, because this definitely won't have any effect on the particular grid, because we can't control the voltages across the whole network simply by controlling the first 3 nodes of the network. This should be logical, and the equality constraints, we don't have any equality constraints. The genetic algorithm options. So this is from my experience that it's always better to increase the number of population, the size of the population. So that's why I've used the size of the population 500, and the maximal number of generations is equal only to 200, because that's enough. You will see that the algorithm will converge in just 500 steps. So when the population size is equal to 500, it will converge much faster than when the number of generations is higher. So now let's take a look at the fitness function. So the fitness function basically does the same. It takes the phase flag and takes the pilot nodes. So it takes the pilot nodes and it loads the data for a particular phase that we are simulating. What it does, it just runs the 9 scenarios which we are going to using, and it determines, of course, the objective function. So the load scaling coefficients, because we have 9 scenarios, I consider the off-peak load, which is equal to 50% of the nominal load. I've used the peak load, which is equal to 100% of the nominal load, and a middle scenario, which corresponds with 75% of the peak load. The solar scaling coefficients, so these are the coefficients which are used to generate the solar scenario. So we consider one scenario, one which is there is no PV generation, the other which is when there is a nominal PV generation, and the middle scenario which contains 50% of the PV generation. So at the very beginning, we need to, of course, initialize the objective function, and basically what we do, we just have 2 loops, one looping through the load scaling coefficients and the other looping to the solar scaling coefficients. And for each of these scenarios, so we combine 0.50% of the loads with 0 PV generation, 50% PV generation, and 100% PV generation. We just simulate the sensitivity control technique for each one of these scenarios. Basically, the sensitivity control function, which I've talked about earlier, takes the pilot nodes, so it takes the locations of the pilot nodes, it takes the load scaling, so it scales the loads according to the scenario which is being simulated. It scales the solar generation according to the scenario which is being simulated, and it takes the data, of course, on the network. So it takes the values for the lines, loads, and the values related to the PVs and to the inverters. And this sensitivity control function, let's take a look at what it does. The most important thing to consider is things that needs to be done is to conduct a Newton-Raphson load flow. And why is that done? Because we need to determine these these sensitivity matrices, SLL, SLG, SGL, and SGG. Basically, I've told you earlier that the S matrix is equal to the inverse Jacobian matrix J4. So basically, we just conduct a Newton-Raphson load flow, we let it converge completely, and we take the value of the Jacobian of the matrix J4, of the submatrix J4 from the last iteration. So that completely corresponds with real J4 matrix. And basically what we do, we just say that the sensitivity matrix is equal to the inverse J4. After that, what we need to do is to take the is to determine these submatrices SLL and SLG, which is pretty easy because the nodes are already divided. If we take a look at here, so it was done in advance to divide these matrices into the matrices corresponding with the loads and the matrices corresponding with the generators. This was done in advance simply by renumerating the nodes. So if we take a look at here, so we sorted and we renumerated the nodes, and the nodes are renumerated according to the node flag. And the node flag, let's for example run the code, and still let me just show you what the node flag is. Yeah, so the node flag, if we open it, it has the values from 1 to 3. And you can see that 1 is at the start and everything else is 2, all the way till 3. And the value 3 starts only after 2. So this means that the first node is a slack node. All of the other nodes are PQ nodes. So these are PQ nodes, these are load nodes. And then we have the control or the generator nodes, which are the last 10 nodes. So this is already done in advance. So the matrix has been already divided into the matrix corresponding with the loads and the matrix corresponding with the generator. So that's already done in advance. Now we just need to take the submatrices SLL and SLG, and we need to create the C matrix, which is used to determine the voltage deviations of the pilot nodes. That is pretty easy. So basically we just loop through the matrix and we use this equation here. So basically if the bus J or the node J is equal to should be the ith pilot bus, then the value is equal to 1, and otherwise the value is equal to 0. Apart from that, we just now use the C matrix to create the matrices B and M and B, and easily we just determine the operation of the generators in order to neutralize the delta QL, which are the changes in the reactive power of the loads. Of course, the generator reactive power or the changes in the generator reactive power need to be limited in order for the generators not to exceed their rated power. So we need to limit the power, the changes of the PV's reactive generation in order to assure that the nominal power of the inverter is not changed. So this value QJ max, so this is the maximal reactive power of the generators, is given here. So at the very beginning we calculated using the nominal inverter power and using the current PV generation. So basically you can see that if there is no solar scale, so if solar scale is equal to 0, that means that it's a cloudy day, we don't have any generation from the PVs. That means that the whole power of the inverter can be used to generate reactive power and to help the grid out with voltage regulation. After that, we just use the equation which is described in the paper. So SLL times delta QL plus SLG times delta QG to determine the, so this is the delta VL vector, which is given here, and we just sum that vector. So we just sum that vector in order to determine the changes across the network. Now we just return this value to the fitness function. So we return the value to the fitness function, and the fitness function just adds that value, delta VL. So it just adds the square of delta VL to the objective function, and this is run through all different 9 scenarios. And for a single pilot node, so for a single combination of pilot nodes, we get the value of the fitness function. So that's basically it. That's the whole logic behind the algorithm. I don't think that you need to generate all of these pictures from here, because your paper is not considering the selection of the pilot points. Rather, you're just using the selection of the pilot points as the input to your algorithm for the voltage control. What I would do on your place, I would just leave a single paragraph, for example, like this one half of the page, where I would just describe the procedure, which I described on the beginning. So I would describe this procedure here, and not use these matrices. So this is pretty hard to understand. Rather, it's better to use the values and the names of the variables that I've been using. So just explain what you've done and show the combination of the pilot nodes, and you don't need to do anything further. You just use that as an input to your code for the voltage control of for the reactive power curtailment and active power curtailment of the PVs. So now let me just show you how the algorithm works. Basically, we just run the main function. So we just run the main function, remove the breakpoint, so continue. And the algorithm starts running, and you can see that in our case it already found a nice value of the reactive power changes. So it converges pretty fast because the search space is discrete. So we have a search space which only has the combinations, and it has discrete values of the nodes which can be selected as pilot nodes. So our algorithm converged, and it returned the combination of the pilot nodes which gives the best results. So as the pilot nodes 1, 6, 78 have been taken, and basically these nodes of the phase A should be selected as the pilot nodes. What you need to understand that this is not node 1, so because the nodes are renumerated, so the true indexes of the nodes which are going to be used need to be determined using the nodes, the renumeration which we've used here. So because the nodes have been renumerated, so we need to determine these PQ nodes. So these are the PQ nodes of our grid. So let me just show you that. So these are the PQ nodes, and if we open them in the workspace, so these are the nodes of the network which are considered as PQ nodes. So we have 90 PQ nodes in the network, 11 control nodes, and 1 slack node, which corresponds, which means that that's the number of nodes we have, and the nodes which are real control nodes are obtained as PQ nodes of X, and these are the nodes which are selected as the pilot nodes. Furthermore, these values also are not true IDs of the nodes. So I will show you. I will make a script which will do all of this for you, so you don't have to do this every time. Basically, that's it. and you just use these values of the pilot nodes for the for the code which I've done earlier. So that's it. If you have any questions, feel free to contact me, and that's it.